Welcome to my channel, JaberTime. Today I'm going to go over the divergence theorem. Let's get into it. We start with the Green Theorem. The Green Theorem starts on a plane x and y, closed path going counterclockwise. If the function or the vector field is defined as pi plus qj, the line integral along the closed counterclockwise curve C, or of f dot dr, is the line integral of p dx plus q dy, or differently, it becomes the double integral over the region D, which is controlled by the closed curve C, of dq dx minus dp dy dA. This was covered a few videos ago in detail with some examples. Green's theorem in vector version, when the vector fields are on r to the second, the line integral becomes f dot n ds, which is the double integral over the region D of the divergent of f xy dA. Green's theorem in vector version on r to the third, as you could see, we have a region E in 3 dimension. We have the normals, and we have the surface S. It becomes the divergent of f over the space region E, dV now, not dA. The divergence theorem is another form to Green's theorem in 3 dimension, states that under the given conditions, the flux of f across the boundary surface of E is equal to the triple integral of the divergence of f over E. Find the flux of the vector field f equals zi plus yj plus xk over the unit sphere x squared plus y squared plus z squared equals 1. Well, first we need to find the divergence, since this is our topic. The divergent of f will be ddx, ddy, ddz of the first, second, and third component. The derivative of this with respect to x is 0, derivative of y with respect to y is 1, derivative of x with respect to z is 0, so just 1. This is a quick example. The unit sphere S is the boundary of the unit pole B, given by x squared plus y squared plus z squared is less than or equal to 1, as you could see from this graph. So, the double integral over the surface S, which is the unit pole, dot ds, is the divergent of f dv over the region E, but in this case the region E is the unit pole capital B. But the divergent was 1. Right here, sorry, I looked at the wrong one. So we don't need to integrate here and use spherical coordinates. We just want to find the volume of a unit pole, as you could see. So it's a volume of a unit pole. We don't need to integrate, which is 4/3 pi r cubed, and r is 1. And that's the answer for this problem. It's a quick example. Nothing much about this. It's just like a quick example. Find the double integral over the surface S of f dot ds. Here's a different vector field. S is the surface of the region E, bounded by the following: the parabolic cylinder z equals 1 minus x squared. It's kind of like a little bit maybe confusing when you call it parabolic and cylinder, but you know what says z equals 1 minus x squared. It's like minus x squared. So looking at the z and the x coordinates, it's pointing down on the negative z direction from the point of the x point of view and shifted up to 1 unit. You don't have to graph it. I'm just saying like why they call it parabolic and cylinder, because it's kind of like going around. When they mention parabolic cylinder, they also, you could think about the polar form later on in case if you need it. Staying focused with the problem. So the planes z equals 0 and the planes, sorry, by the parabolic cylinder. Yeah, that's when you go off and you didn't stay focused on the notes. With the plane z equals 0, that's the xy plane. Y equals 0, that's the xz plane. And the plane y plus z equals 2. So imagine if you don't see the z-axis and you are between the y and z, that's kind of like a y-intercept concept graph. Crosses the y at 2 and crosses the z at 2. Let me show you the graph. First of all, looking at this right here, ignoring the y, you are seeing a parabola. You see that? Starts here, goes up and back down. Up to 1 because it's shifted up 1 unit. Because y is loose, it doesn't have any restrictions, you could stick it out. And you could see that it's kind of like a tunnel. Alright? Z equals 0, that's the xy plane down here. Y equals 0, that means the xz plane right there. And this is y plus z equals 2. This is part of it. So if you extend this all the way up, it's going to cross at 2 here. And it did cross here at 2 on the y-axis. So that's our graph. Now, for this problem, we have S1 plus S2 plus S3 plus S4. If you noticed, I mean, this portion is one surface. This one to the right is one surface. In the back, there's another surface. At the bottom, there's another surface. So we could think about it this way. But what comes in handy with this section is the following. Instead, we use the divergence of f. We have the vector field given to us right there. All what we need to do is follow the steps and do it. Find the divergence of this vector field f. We know how to do it. We find the derivative of the first one with respect to x, and we end up with y by itself, and we move on with respect to y with respect to z. The last one is 0, of course. Now we have y plus 2y, which is 3y. Now next, we use the divergence theorem to transform the given surface integral into a triple integral. Instead of staying on the surface from one side to the other side, we could just integrate a triple integral inside. So it's kind of like, as you could see, Green's theorem in 3D. Green's theorem took you from a line integral to inside the region D. This one takes you from a 3-dimension. Instead of staying outside on the surface, you could find the integral, triple integral of the inside region, which is called E. That saves a lot of time, by the way. I mean, it's like, I know you're doing triple integral still, but imagine if you do it for each surface, 4 surfaces. So we have f dot ds over the surface becomes the divergent of f dv over the region E. Well, the divergent of f was discovered to be 3y, and now we have 3 outside, y dy, dz, dx, going from y1, which is 0, that's the xz plane, to y2, which is this right here, going this way. That's 2 minus z. As you could see, this is y2 for us now. Then after that, we're going to go dz. dz goes from down, which is 0, all the way to the top, and this top right here is 1 minus x squared. That's right there. Finally, the constants, which is dx, and dx goes from all the way back here, which is -1, all the way to this point, which is +1. Integrating y with respect to y, that will be y squared over 2. Plug in 2 minus z, that's why 2 minus z to the second over 2. Of course, 0 is going to cancel. Integrating this with respect to z, you could do it with u substitution, calling 2 minus z as u, and you move on. A minus sign will show up, as you could see. Then after that, you integrate with respect to x after you plug in the numbers. Let's simplify it first. 2 minus z, where z is 1 minus x to the second, then you cube it, you multiply by itself 3 times, and you end up with the following, reducing your steps, and getting to the point. With respect to x, from -1 to 1, this -half is part of the game that simplifies 3 here and 2, and the negative goes outside. You end up with 184 over 35, and that should do it. Thank you for watching, and we'll see you next time. Thank you. Thank you for watching. Don't forget to hit the like button, subscribe to see some more, and I'll see you in the next one.